today's video, I'll talk about the propositional logic. So, proposition is a declarative sentence, a sentence that states facts, and you can answer it either true or false. So, for example, Rodrigo Roa Duterte is our president. So, the sentence is a proposition because it states fact that Mr. Rodrigo Roa Duterte is our president. So, the propositional logic is the area of logic that deals with the propositions. The common variables that is being used to represent the proposition is P, Q, R, and S, and it is called the propositional variables. Compound proposition is constructed from the logic connectives, and other propositions. So when we talk about compound proposition, it is composed of two propositions that is being connected, such as negation, conjunction, disjunction, implication, and biconditional are being used to connect two propositions. In order for us to create a truth table, we need to have these two compound propositions. So first thing we will do is we need to identify how many propositions that we have. So we have P and Q. So 2 is raised to 2 is 4. So we have 4 proposition. So we need to create a table P and Q. The value for this thing is truth, truth, false, false. Then for Q, we have true, false, true, and false. So the next thing that we will do is we need to get the true the value for negated P, since negation is first in the order of precedence. So we need to negate this P, and we need to find the value of negated P in this. So since the first value is true, and if you negate that, that will become false. Same for this thing, it is true and it become false. Since it is false, it become true, and same for this thing. So the next thing is the negated Q. We will negate the value of Q. Since it is true, it becomes false, and since it is false, it becomes true. Same for these two, remaining two. Since it is true, it becomes false. It's false, it becomes true. So the next thing we will do is we need to find the truth value of these two. So since we have the proposition, this is called biconditional. So in biconditional, we can only put true if the two proposition has the same value. So since negated P and negated Q has the same value, so we will put true. I forgot to put this thing, negated P and negated Q. So since they are the same value, I put true. Next, false and true. Since they are not the same, I will put false for this thing. This thing is true and false. so it is false. True and true, it is true. So the next thing we will do is to get the truth value of this one, P and Q. We will get our answer in this. So since they are the same, well, since they are the same, by conditional, we will follow the things what we have done in this, but we will get our truth value here. So since they are same value, we will put this true. Since they are not the same, true then false, we will put false. Last thing is the third thing is false then true, so it is false, then false and false, it will become true. So the last part for this is we will answer this two compound proposition, this thing, this and this. And since this is implies, and since implication and biconditional for me is this has the same rule, so in implication also we can only put true if the two values has the same value. So first we need to put first the problem, this negated P conditional negated Q implies is P and Q, P Q. So since they are both they are same value, so we will put true. Since they are both false, they're the same value, we will put true. Same for this, they are false, same value, true. And the last thing is true then true, so the answer means true. This is the truth table for these two compound proposition. So in this video, we will transform logical expression into a logical sentence. First, we have two proposition, the P and Q. And P is I bought a lottery ticket this week, and for Q, I won $1 million jackpot on Friday. So first, we need to get the equivalent of our connectives. So in negation, the equivalent for negation is not. For this junction is or. For this junction is and for implication is if and then. In biconditional is if and only if. So our first logical expression is negated P. We will negate P. We will negate this. We will negate this statement. We will negate P. So the negation for this thing, I bought negation for this statement is I bought a lottery ticket this week. So if you negate it, that will be I will I did not bought a lottery ticket this week, because you will negate P, and P is I bought a lottery ticket. If you negate that, that will be I did not bought. So you did not bought a lottery ticket this week, because the P here is you bought a lottery ticket this week. So our next logical expression is the conjunction of P and Q. The conjunction of P and Q. So here we will just connect these two sentence, the two proposition, or these two sentence, using our word, using the equivalent of disjunction or. So we will put first the P. I bought a lottery ticket this week, and the conjunction or I won the million dollar jackpot on Friday. So that is the equivalent of this conjunction of P and Q. And our next logical expression is implication of P and Q. So we need to implies the value of P and Q using these words. So we will implies these two proposition, and the words that we will be using is if and then. So we will put if I bought a lottery ticket this week, then if and then I won the $1 million jackpot on Friday. Here use the value of implication in words, the if and then. So our fourth logical expression is conjunction of P and Q. So we'll use the word and because it is equivalent to conjunction. We will just connect these two proposition, and the word will go like this: I bought a lottery ticket this week, and the conjunction, the equivalent for conjunction, and I won the million dollar jackpot on Friday. So our fifth logical statement is biconditional P and Q. So in biconditional we'll use if and only if. So the words will be go like this: I bought a lottery ticket this week, if and only if. So the value for biconditional ay the equivalent value ay equivalent value of biconditional. If and only if I bought I won the million dollar jackpot on Friday. So our sixth logical expression is negated P negated Q. Implication of negated P and negated Q. So first we will negate these two propositions. So the negation for this one is I did not bought a lottery ticket this week, and for this one is I did not won the $1 million jackpot on Friday. So we will implies it using negation, if and then. So the words will go like this: if I did not if I did not bought a lottery ticket this week, then and this if then I did not won the $1 million jackpot on Friday. If I did not bought a lottery ticket this week, then I did not won the $1 million jackpot. So our last logical expression is P Q. Conjunction of negated P and negated Q. Since the first we'll negate these two just like we have done for this. I did not bought a lottery ticket this week, and I did not won the $1 million jackpot on Friday. So we will use since it is conjunction, we will use the word and. So the words will go like this: I did not bought a lottery ticket this week, and the conjunction and the equivalent for conjunction, the word and, I did not won the $1 million jackpot on Friday. I did not, so we negate the value of P, which is I bought a lottery ticket this week, and if we negate it, I did not bought a lottery ticket. Same for the proposition Q, I did not won the $1 million jackpot on Friday, and we use equivalent of conjunction value and. Since we have already a problem, this one and this one, it is called bit string or a bitwise. So in order to So now we will get the bitwise of n. Bitwise n. Bitwise n. In order to get the bitwise n, we will transform this thing into this form. So we need to write it first. This one, 1 0 1 1 1 1 0, and this one 0 1 0 0 0 0 1. So in bitwise n, we must put only 1 is equivalent to true, and 0 is equivalent to false. For us to put 1 or a true, the two proposition must have the same value. So since it is not the same value, it is false. Second thing, 1 and 0 not the same value is false. 1 and 0 false, 1 and 0 false, and 1 0 false, 1 0 false, and 1 0 is false. So the bitwise n is 0 0 0 0 0 0 0. This is the value of bitwise n. So the next thing is bitwise OR. We need to follow the steps or form. We need to follow this form in order to get the value of OR, bitwise OR. So we will copy this one, 1 0 1 1 1 0 1 0 0 0 0 1 0. So in bitwise OR, we can only put 1 if one of these two proposition having a 1 or a true value. So this one, 0 and 1, since the second proposition has a true value, we will put true, which is 1. Second thing is has one true value, we need to put 1. Same for this thing, true. Same for this, so true. This thing, true, then true. This is the value of bitwise OR. So the next thing is bitwise ROX or exclusive OR or SOR. Sorry, SOR. It's SOR. SOR or SOR. In order to get the bitwise SOR, its value, we need to follow this thing also. 1 0 1 1 1 1 0 0 0 1 0 0 0 0 1. In bitwise SOR, we can only put true if the two proposition are not the same. So if we say 0 0, so the value for this one is false because SOR say that we can only put 1 if they are not the same value. So this one, 0 and 1, since they are not the same, we will put true or 1. Same for this one, they are not the same, we will put 1. Same for this one, we will put 1. Same for this one, put 1, and the other. So this is the value of bitwise XOR or exclusive OR.